What I wanted to talk about today, we'll see how far we get. I introduced the idea last time of infinite dimensional Hamiltonian systems. So let me just go over that again. And this, the idea here is that we can write PDEs that come from mechanics. So PDEs related to the motion of a continuum or medium, like a fluid, solid, or a plasma, or even Maxwell's equations, which just describes the electromagnetic fields. The governing PDEs can be written as coming from a Hamiltonian system if you write things in the proper setting. And so this setting is having a Poisson bracket that follows all of the properties we've talked about before of a Poisson bracket. And then you could write in terms of this canonical or non-canonical, I'm sorry, Hamiltonian form, where you look at the evolution of scalar fields. And if you can write an equation that looks like this, then you have a Hamiltonian system. It may be non-canonical. So this requires an appropriate definition of the Poisson bracket and appropriate H. Oops. And if you can do that, you've got a Hamiltonian system. What's so great about that? Well, the PDE then inherits all of the nice Hamiltonian structure that we've been talking about for several weeks, and any finite dimensional approximation that arises from that PDE, for example, like a wave solution or some other solution, also inherits that Hamiltonian structure. So there's a particular simple example that has been used by others to describe this, and it's a version of the Shallow-Water Equations that describes tsunamis. It's the Korteweg-de Vries equation, and it admits Soliton solutions. The PDE, it's just a PDE in one spatial dimension and also time. So we're looking at U, which is a function of X and T. This is the vertical displacement of water from an equilibrium. And to be physical, this solution, it goes to equilibrium. Everything goes to zero, including the derivatives out at infinity. And the PDE looks like this. So we have a part that depends on time. We've got a nonlinear interaction part. And this all comes from the Navier-Stokes. This can be derived from the Navier-Stokes equation. And then we have this other part, which is like a dispersive piece. You might be wondering, where does this number 6 come from? It's just from non-dimensionalizing in a certain way. So this is non-dimensionalized. U is non-dimensional, X is non-dimensional, and T is non-dimensional. One of the key things about this PDE is that it admits nonlinear, non-perturbative Soliton solutions. These are shapes or waves that propagate without changing. So they don't just naturally flatten out as they move along the way waves typically do. They can propagate without, in some sense, losing strength, losing energy. And this was seen, I think, originally by an engineer in England looking at the motion of waves in a canal. But we now know that this is also an approximation for how things move through the ocean. And that's, we call them tsunamis. So I'm going to say a little bit about that. How does this PDE get cast into this form up here? And then maybe I'll mention quickly some other systems that can be written, PDEs from mechanics that can be written in Hamiltonian form. And then we will go on to another topic. So the Shallow-Water Kdb equations. Let me just repeat it here. It's not that. 6 u partial x. Then this triple derivative, third derivative of u with respect to x, equals 0. So this describes how some kind of, it's the surface of the water and how it varies with respect to the equilibrium. So you might ask, how, in what sense is this Hamiltonian? Well, we have a language for that now. We know that it's not described by Q's and P's, but we have this sort of larger definition of casting things in this form, that if we have some scalar function, f, its evolution with time is described by a Poisson bracket of f with h for an appropriately chosen h, plus if f depends explicitly on time, we add that piece. Okay. So we're going to show that we can cast things into this form. So we'll show that the KdV equations can be written in this form. And the phase space here it's the space of all possible u as a function of x and t. So it's the space of all possible functions u that depend on two variables. So we have something that's infinite dimensional, meaning at every point x, we've defined a u. Not only that, at every point x and t, there's a u. So there's this is infinite dimensional. So the Poisson bracket the PV will be defined in terms of functionals. So this kind of harkens back to when we did the variational approach to get the equations of motion. So a functional, I don't know if I called it that then, but if you have a functional, capital F, it's a function of a function. So the way to make capital F a scalar is you integrate. So integrate over the entire spatial domain something in here. So we have to choose something for the integrand, which is going to be some function of u and or its derivatives. And here, and I do not know the history if this was found through trial and error, but I'll just give you what the Poisson bracket is, and it's written in terms of functionals. So the Poisson bracket will be, remember, it's defined over some space. The Poisson bracket of two things gives you another thing of that type. So the Poisson bracket is over the space of functionals. This is a functional. It takes in this function of x, and you integrate over x and get a number. Or I guess you'll get something that could be a function of time. So the Poisson bracket will be defined over the space of functionals. I have to turn on my heater because I've got neighbors, and they're, so we can drown out the sound of the neighbors. My neighbors, I think it's the wrestling team, and they're having a party. It's what, Tuesday? Almost 4. Okay, so yeah, here's the Poisson bracket. And I will give it the notation, so I'll use capital F, capital G. And just to remind us that this is specifically for the KdV equation, I'll put that little notation. So this is the Poisson bracket for the KdV equation. It's an integral, and if I don't specify the limits, this is an integral over all of x of these functional derivatives. So this is functional derivative of f with respect to u times the partial derivative with respect to x of the functional of g, functional derivative of g with respect to u. And if you're like, what are these? Well, we saw them in an earlier lecture, I believe, when we talked about variational principles. So delta f delta u is the functional derivative. So I did. I think I talked about these in an earlier lecture. Can you just click yes if you remember me saying something about these in an earlier lecture? Yeah. Okay. Good. I don't remember when it was. Probably sometime in February. And I don't remember the date of the lecture. But it was an earlier lecture on variational principles. And I'll just give you some examples. There's a, I think in that earlier lecture I covered a way to find what these are. Actually, let me make some space for myself and just define it again. You define it the way you would define a derivative. So limit as epsilon goes to 0, 1 over epsilon. It's this functional u plus epsilon and then some kind of test functional v minus functional of u. If you take that limit, and then you will be left with something that looks like the integral of something times the test function v, and that something is the functional derivative of u. So that defines it. So this v is an arbitrary test function. And so this procedure defines the functional derivative. Okay, so let me give you some examples of what this procedure gives you. All right, here's f. If f of u is, let's just pick something simple. The derivative, the integral over all x of just the function u, okay? Then we can define fu plus some small scalar epsilon times a test function. And this just looks like dx of u plus epsilon v. Or we could split this up and look like dx u plus, we could pull out the epsilon out of the integral over x of v. Okay, so then 1 over epsilon f u plus epsilon v minus f of u. We could see what this is going to give us. It's going to give us 1 over epsilon, and then this square bracket thing. We'll be left with, right, this looks exactly like f of u. So we'll have fu minus fu plus epsilon integral over x v. Notice these epsilons cancel, and we're left with little dx v. And there's an implied 1. It's implied that there's a 1. So for this f, the functional derivative of f with u equals 1. And you could do that for if we tried something else. So if you try f of u as the integral over x of u squared and did this procedure, you would get the functional derivative with respect to u is 2u. And so on. I mean, you could have things where f is a function of u times partial u partial x and go through the procedure. Okay, well, and if you want to just go crazy with that, one of the homework problems is related to looking at that. The KdV, so the shallow water equations, KdV Hamiltonian, right? It needs to be a functional. It's on the same level as everything else. So to show up in an equation that looks like this, with the Poisson bracket here being the KdV Poisson bracket, we need h needs to be a functional of u. And here is a function that works. So here's the Hamiltonian. It's the integral over all of space of 1/2 partial u partial x squared minus u raised to the third power. That's it. It does not look like kinetic energy, and it's not kinetic energy. But with this Hamiltonian and the above KdV Poisson bracket, the governing PDEs above are equivalent to f dot equals f with h KdV. Now, if we were to take the functional derivative of h with respect to u, this is what we would get. We'd get minus 3u squared minus second derivative of u with respect to x. You have to keep in mind when you do these integrals, if you do integration by parts, you need to keep in mind that the u and all of its derivatives go to 0 at infinity. That's important for evaluating this. It's kind of like a boundary condition. So we've got that for the functional derivative of h, and then if you want to see that this is equivalent to the above PDEs, use as f the f that we had above, dx of u, and then this leads to f dot is the integral over all of space of partial u partial t. And what will you get? You'll get, so f dot equals, saying f with h, Poisson bracket. This will be, the left side gives us dx, partial u partial t. The right side gives us dx, and remember with this f, just like we found above, functional derivative of f with u is just equal to 1. Based on what we wrote up above, we've got functional derivative of f with u, which is just 1, times partial derivative with respect to x of the functional derivative of h with u. This gives us, this is where the 6 shows up, so minus 6u partial x minus third derivative of u with respect to x So now let's just put everything on one side. Let's bring it all to the right side. Dx partial u partial t plus 6u partial x plus triple derivative of u with respect to x equals 0. And for this to equal 0, the integrand must equal 0. And so this is the KdV equations. That was quick. You can verify it. So that is the sense in which the shallow water equations are Hamiltonian. And like I said, why would you even want to explore that? Because if something is Hamiltonian, then it may have one of those, or at least an analog of one of those interesting properties we've talked about before that's Hamiltonians can have. One of those was a system could be completely integrable, meaning if you had and we said that in terms of kind of the usual canonical Hamiltonian, if you had an n degree of freedom system, if it's completely integrable, that means it admits n compatible constants of motion. Well, it turns out these shallow water equations are completely integrable. And so if this is infinite dimensional, it's like n equals infinity. And so there are an infinite number of constants of motion. So this system is not only Hamiltonian, but it has one of the kind of best properties you could have to make a Hamiltonian system kind of solvable, which is that it is completely integrable. Integrable. Which means in this case, because it's infinite dimensional, it has an infinite number of constants of motion. Or if you want conserved properties. And you can even start enumerating them. And that is what the homework question is about. Often they're written in a sequence. So here's like the first one. We'll write it f sub 0. And this is just taking the integral over u, which is the same as total mass. So this is conserved. This integral is a constant with time. It's the same as total mass conservation. If you think of it, it's like there's just as much mass above that equilibrium line as below. The next one is 1/2 u squared, which you can, this isn't total mass, this is the total energy. So if you were to calculate this integral at each moment in time, both of these, you would see that they remain what they were initially. So if you just kind of used your favorite PDE solver on this set of PDEs up here, you could numerically verify that certain things are constant through time, and it's these things. So that's F1. F2 is just the Hamiltonian, which is not the energy, it's just the Hamiltonian. And I don't know how to interpret that one. It's obviously conserved because, right, if you have a Poisson bracket of any function with itself, it has to equal 0. usually H is the total energy, but not always. So that's conserved. And then all the way down, right? It just keeps on going. And these integrals are all compatible. So these, we said before, that means that the integrals are in involution. These integrals, or conserved quantities, are in involution, which means that if you take the Poisson bracket of any one with any other one, and we've got to use the KdV Poisson bracket, you will get 0 for any I and j. And there's an infinite number of them. So good luck verifying all of them. I think for the homework, you're asked to go through F0 through F3 or something. Now, before mathematicians got too excited, apparently it's pretty rare for a PDE to be completely integrable like this, as far as we know. This is the prime example. There may be others out there, I don't know. But this is it. I got excited. I saw a math, one of the math seminars last year. It was somebody trying to write the equations of motion for the atmosphere, and they came up with a way to do it in a Hamiltonian approach, which then led me to ask, well, does that mean, is it a possibility that the atmosphere, right, and all of its complexity is completely integrable? And I think he had some proof that no, it's not. The atmosphere is not. The shallow water equations, yes. But it is still interesting that if you could write the equations of motion for the atmosphere in a Hamiltonian way, that lends itself to different kinds of analysis that could be insightful. All right, I wanted to, I could say something about the Soliton solution, because that's kind of the most interesting. It also relates to this idea of being Hamiltonian and simplifications inheriting that Hamiltonian structure. So I'll do this in blue. Soliton, there's a Soliton solution to these shallow water equations. And we'll just note it's a finite-dimensional solution, solution that inherits the Hamiltonian structure of the PDE. And it comes from a finite-dimensional approximation. So let me just repeat here what the KdV, the shallow water equations were. Partial u partial t plus 6u partial x plus third derivative of u with respect to x. And I'll call that equation star. Now, if you've done anything with PDEs that you think admit a wave solution, one common thing to do is you assume a wave solution, and a wave solution has a certain structure that relates. In this case, we've got u, which is a function of x and t, but a wave is going to be a function of something that combines x and t. Usually with there's a wave traveling where you go a certain amount distance x in a certain amount of time. So we will assume, let's assume a traveling wave solution. That's, as opposed to a standing wave like a string where it's bound on both ends and it just stands there. A traveling wave is like water waves, it moves. So the traveling wave solution would be, we're writing u, as a function of x and t, as some function phi that combines x with t. So we're at x minus ct. So it's just a function of one variable s, where c is the wave speed, constant wave speed. So if you haven't done this before in your life, this is not the earth-shattering. This is not earth-shattering. This is something you would just do. So then you've got some phi as a function of just one thing, one variable s, and we don't know what that thing is. We would just know that it's traveling. So s is x minus ct, and we just now write these derivatives, these partial derivatives, but in terms of s. So partial u, partial t, would be derivative with respect to t of phi, which is a function of s. So this just becomes phi prime, right? The derivative of phi with respect to its argument times ds dt. And what's ds dt? It is negative c. So we've got negative c times phi prime for that. And similarly for partial u, partial x, and partial the triple derivative of u with respect to x. So from the KdV equation, we get the following. From the KdV PDEs, partial differential equations, we get the following ordinary differential equation. And ordinary differential equations are infinitely easier to deal with. So that triple prime means just triple derivative of phi with respect to its argument. We've got this, plus this inherits all of the boundary conditions, with all the boundary conditions needed to be physical. Which would be phi and all of its derivatives forever and ever go to 0 at s goes to plus or minus infinity. So all the derivatives need to vanish. So this is a lot easier to deal with. This is an ODE for phi, for the wave solution. And like its PDE, its parent, this daughter inherits the Hamiltonian structure. So this ODE actually comes from a Hamiltonian. Which means it's Hamilton's equations. This ODE comes from a Hamiltonian, the typical kind of Hamiltonian. H, phi prime. So here phi plays the role of Q, and phi prime plays the role of P. So this is now just the usual Hamiltonian. And this looks like 1/2 phi prime squared. So it looks like the kinetic energy term, and then a potential energy terms. So this is a 1 degree of freedom Hamiltonian, canonical, in fact, Hamiltonian for phi as our variable. And the phi is the dependent variable. The independent variable in this case would be s, right? S plays the role of time. So if you take Hamilton's canonical equations, and you would get, if you were to write it in first order form, you get phi prime equals v, and then v prime equals c phi minus 3 phi squared. So this defines a, you can get a phase portrait from this, a 2D phase portrait, a phase plane. So this is now in first order form. This is what you get. And if we were to plot it, let me just try to sketch out what you would get. So along one axis, we've got phi, and then the other one is phi prime. This actually has 2 equilibrium points. So there's 2 equilibrium points. One of them is the origin, and then another one is at c over 3, 0. So there's an equilibrium point here, and then an equilibrium point here. C over 3, 0, and at the origin. And just like we would do with any simple 1-degree freedom Hamiltonian system, we don't even have to solve that. We could just look at contours of H. Contours of H, and that'll basically give us the phase portrait. So there'd be here's some contours of H sketched out, and then there's a contour that passes through the origin, and it's kind of weird. It kind of ends there. That's because the origin is a saddle point. Which way are things going? Yeah, probably going that way. And then we've got other solutions. So H equals 0 contour is this one, the one that passes through the origin. And that's really the only one that matters. You might say, why? It matters because it's the only one that matters because to satisfy the boundary conditions, and let's just think of 2, phi equals 0 and phi prime equals 0 at s going to plus or minus infinity. The only thing that happens for is either the origin itself. The origin itself is just total equilibrium. Nothing is happening. So it'd be like a wave of no height, doing nothing. Or this trajectory, this part. If you start anywhere along here, then going backward in time, you'll stay on here and you will asymptotically approach the origin. So this is going there as s goes to negative infinity. And if you go forward, then you're approaching the origin as s goes to positive infinity. So to satisfy the boundary conditions, only one, and I don't know if I've used this term before, homoclinic trajectory, meaning it asymptotically approaches the same equilibrium point in forward and backward, in this case time is s. So only one homoclinic trajectory is a possible non-trivial solution. The trivial solution would be the origin itself. okay? And you can analytically get what phi as a function of s is, and that gives you the basically the shape of the soliton wave. And if c is positive, that means it's going this way. If it's going to the left, then c is negative. But for each value of c, there is some shape. And I think I have already calculated some of those, maybe. Yeah, well, here's actually the phase portrait. So if I just kind of naively took that set of first order ODEs and plugged it into P-plane in MATLAB, this is what I would get. And here is one of the Soliton solutions. So you see, it looks kind of like a, I mean, it looks like a bell curve. It's made up of hyperbolic secant and things like that. Should I show this? This is just showing some solitons. Here's a soliton. Here's two solitons. You start here looking at the bottom. This is showing x and time. And this is two solitons moving to the right, but kind of the short soliton is moving slowly to the right. The skinny, tall soliton is moving quickly to the right, and they pass through each other. So that's one of the things about solitons is they are like particle-like solutions. I don't know if I mentioned that here. Yeah. Yeah, you could learn more about them if you're interested, but I wasn't going to cover it too much. And I don't know if there was a homework problem related to analytically getting that or not, but one of the key points here is, so we had some PDE that describes something in mechanics, in this case, the height of water waves when you've got some shallow depth, and it turns out to be Hamiltonian. And simpler approximation of that, assuming a wave, also inherited Hamiltonian structure. And from that Hamiltonian structure, we could see certain solutions. And in fact, that's what helps you analytically get the form of the soliton as it's a hyperbolic sign, perhaps. Yeah. And if you want to know more, this is in that one of the chapters that I posted on infinite dimensional non-canonical Hamiltonian systems. It's the Marsden and Ratio, either chapter, I think I did chapters 1 and 3. And it is worth noting other PDEs from mechanics are Hamiltonian. And honestly, I haven't seen this exploited. I feel like the only person who knew about it was my PhD advisor and maybe a handful of others. So I don't know if it's been fully exploited, meaning there could be a lot of rich research to be done. But I think I can show, where is it? Let me look at it. This is one of those chapters. Okay. Yeah, here is an example where the Euler equations of a fluid can be written in terms of having a Hamiltonian structure where you've got the Poisson bracket written in this equation 1.5.5 form. This is going to let me draw. There it is. And there's other things as well. Whoa, I don't want that. the Maxwell-Vlasov system, this is related to plasmas. And that can be written, so this is the evolution of a plasma. It's like another phase of matter. And that can be written in terms of as Hamiltonian, if you find the right Poisson bracket. Maxwell's equations, which describe how electro and magnetic fields evolve in space and time, are some very famous PDEs in physics, and you could write those as coming as Hamiltonian. This is the Hamiltonian. Look, it's like 1/2 the magnitude of the electric field squared plus magnetic field squared, with this right here as the Poisson bracket, which I think has some simpler way that it could be written in terms of curls of vector fields. I know these things that look like delta F, delta of a vector. Those look scary. Yes, they do. But there are ways to write them. And just the fact that Maxwell's equations are Hamiltonian, there's probably a lot of rich insight that could be gleaned from that for someone who's interested in it, but has yet to be done. So leave that for future work. It won't be in a homework, but it's just good to know. Put that in your back pocket.
A couple of questions. Oh, sorry.
Yeah,
so first of all, is the can you write the K and V Poisson bracket in terms of the traditional non-canonical Poisson bracket form that has an omega matrix? Or is that just a Poisson bracket that fulfills the properties of the abstract algebra properties of being a Poisson bracket and is therefore considered a Poisson bracket? Like, I guess my question is, can all Poisson brackets be written in that omega form mentioned earlier, or is this an example of an exception?
are you asking, is there something special about the form of Maxwell's equations?
No, not Maxwell's equations. So you know the K and V, you defined the K and V Poisson bracket.
Yeah.
And can that Poisson bracket be written in terms of the non-canonical form of the Poisson bracket that you mentioned earlier, where there's an omega matrix in the middle? You know, the canonical case, of course, just uses J, if I recall correctly. But the non-canonical case has a general omega matrix.
I see. That might only be for finite-dimensional non-canonical systems.
Okay. All right. And then my other question is, if you have an otherwise Hamiltonian conserved canonical system, like finite-dimensional, and you add in like a dissipative or perturbative force, is there still a good chance that it could be written in Hamiltonian terms using a generalized non-canonical Hamiltonian?
I think that's an open question. I don't know.
All right. Thank you.
Okay. I just realized my earbuds weren't working. Are you able to hear me fine? I think it's just my computer speaker. Okay, good. Yeah, otherwise someone would have spoken up. Yeah, that's a good question. I don't know. I know that you can write systems, you can include any damping force as kind of a non-conservative force, even if we're talking about a PDE, I'm pretty sure. But can you, yeah. I'm just making it more confusing now, so I'll just say, I don't know. I don't know. Maybe that's a project to look into that, to even just find out what other people have done. All right, I wasn't going to say anything more about infinite dimensional Hamiltonian systems. I think there, like I said, I think there's some room there for work to be done, maybe something even related to numerical methods to more accurately or quickly solve PDEs that we know are Hamiltonian, but I'll just leave that for now. So if there's no additional comments, I'm going to move on to another topic. So this is the idea of parametric resonance. So this is more down to earth. It may get a little mathy, but very dynamicsy. And this is, the reference is Hand and Finch, chapter 10. And specifically, this part is 10.2. If I haven't posted that, I will. Just to get us started, we'll look at a simple example. This is looking at the pendulum near equilibrium with a gravity on Earth is constant, to most reasonable degrees, but let's just assume that gravity wasn't. So let's say I was changing G a little bit in time, so that I had G slightly increasing and slightly decreasing. So let me get more precise about what I mean. So we're looking at the pendulum near equilibrium, the bottom position equilibrium. So we could use sine of theta as approximately theta. And this essentially approximates moving the pendulum pivot up and down. So if we took that pendulum pivot, moved it up and down periodically, that would kind of be like effectively changing gravity. So we've got our mass at the end of a string of length L, and we will still consider theta, but we're looking in this regime where sine theta is about equal to theta. So the pendulum equation is just theta double dot plus G over L theta equals 0. And we will change G with time, so that instead of being just constant time, we'll make it change periodically. So we'll increase by some amount, I'll call it delta G, and then we'll decrease delta G. So now G, instead of being constant, is a function of time, and this thing will repeat. So we'll have a certain period of the motion, or period of the moving the pivot up and down. So it's like we've dropped, we go up, right? This is kind of unphysical to just instantaneously change things, but we could eventually smooth it out. So this is a simple model of vibrating the pivot. Pivot of a pendulum. And it's insightful. As I often like to do when I've got constants, I like to get rid of them. So we non-dimensionalize by using, by rescaling. In this case, theta has no dimensions. G over L does, though, has dimensions of 1 over time squared. So we will non-dimensionalize by using L over square root of L over G as the unit of time. So square root of L over G as the unit of time. In fact, maybe I will, instead of writing this as theta double dot, I'm going to write this as second derivative of theta with respect to time. Maybe I don't know what to do. I'll do theta big double dot. So this is dimensional time derivative. Because I want to go to theta dot, theta double dot. These are derivatives with respect to the non-dimensional unit of time. So when we do that, then this becomes now theta double dot plus theta equals 0. Much easier and cleaner to work with. We don't have this G over L stuff. But we will still include the square wave gravity. We'll include square wave gravity. And how is that? We will, so in these units, gravity, the value of gravity is just equal to 1. So here's 1. And here's time. And we will write, instead of delta G, so delta G goes to R, where R is going to be some factor that's small. So this is R, and then this distance is also R, and this thing will repeat forever and ever. We're going to define our units such that, so this is the non-dimensional time. That's kind of confusing, I know. This is dimensional time. What are we going to do? We're going to say that 1/2 period of the square wave is pi x. And so a full period of the square wave is 2 pi x. So what does that mean? That means that the period of forcing, non-dimensional period, is 2 pi x. So including the square wave gravity, this thing becomes actually 2 equations. This is theta double dot plus the slightly increased gravity. And so that is for time greater than 0 and less than half the forcing, or pi x. And then this will become slightly smaller gravity for the second half of a forcing period. And then repeating forever after. So here, what is R? R represents the amplitude of the square wave. So the size of the forcing, if you want. X represents the period, period of the forcing. It's related to, right, 1 over the frequency, 1 divided by the frequency of the forcing. So x equals 1 is the same as the natural pendulum frequency. What if we had x of 0.5, 1/2? That means we're doing forcing at twice the natural pendulum frequency. Etc. I mean, maybe if we chose x to be something irrational, then we get something else. Okay. Well, we know, at least for each of these individual regimes, how to solve for theta. Right? Theta, each of these is of the form theta double dot equals -a theta with a greater than 0. And that's like the easiest second order ODE to solve. We know to define something we call omega squared as a, and then solutions are theta as a function of time is capital A cosine omega t plus b sine omega t. And then if we were to take the first derivative of that, we get negative omega a sine omega t plus omega b cosine omega t. You take two derivatives. You get that. Which you just stare at it and you go, oh, this looks exactly like negative omega squared theta. So, okay, it checks out. It's the same as that. So that means this is the solution, which A and B are related to the initial conditions. Right? Theta at time 0 is equal to A. So A is equal to the initial displacement of the pendulum from equilibrium. And theta dot 0, so just evaluate this thing at 0, and what do you get? You get omega b. So b is equal to it's the initial velocity divided by omega. Okay. Now, what do we want to do? We've got two of these solutions, right? There'd be one for the first half of a forcing cycle and then another for the second half. What we want to do is look at a map that maps an initial condition at the beginning of a forcing cycle to what happens halfway through, and then what happens for the second half. So we're going to construct a discrete map. Since we can analytically write solutions, we should be able to do this. So what am I trying to do here? We want to construct a discrete map from, let's say, theta and theta dot at some initial, at the initial time, so the beginning, to halfway through the forcing cycle. So from time equals 0 to time equals pi times x. So this would be telling us, imagine it on the phase plane. So here is theta dot times equal to 0. Well, this is going to map to some other point, theta dot, after half a forcing cycle. So we'll look at that's the first interval. So that is for the first half of the forcing cycle. Where remember A equals 1 plus R, given what we've written up above. So that means omega is square root 1 plus R. And we can write the analytical solution using what we've got up above. So theta pi x, theta dot pi x equals, and we're going to write it as a 2x2 matrix times the initial condition. So here's a 2x2 matrix times the initial condition. And I'm going to write it this way: cosine, call this capital gamma plus, this is sine capital gamma plus divided by square root 1 plus r. This is cosine capital gamma plus, over here minus square root 1 plus r times sine gamma plus, I'll call this is m plus. The plus is for, this is the plus r part, so the slightly more gravity. And this is just a constant 2 by 2 matrix. I guess I should make a note of what gamma is. Gamma, there's going to be a gamma minus too, so I'll define them together. Gamma plus and minus is just pi x times square root 1 plus or minus r. So that's not pi times, that's pi x. Okay, now for the other half of the cycle, the thing that takes this from here to here, for that part, we've got 1 minus r. For this other part, I'll do it in orange. 1, sorry, yeah, this first part was 1 plus r. And we'll end up at a new location. We'll draw that in red. So that's theta dot at t equals 2 pi x. Now, what is that? Theta 2 pi x, theta dot 2 pi x. We could also write that in terms of a 2 by 2 matrix. 2 by 2 matrix times its initial condition, but the initial condition for that part is the what happens at the where we are after the first half of a forcing cycle. So pi theta at pi x and theta dot pi x. And then maybe you can imagine what's going to happen. We'll take this and this. And we could write what happens after one full cycle in terms of the product of two matrices. Let me first write this matrix. Cosine gamma, capital gamma minus. It has same structure. 1 minus r, cosine gamma minus 1 square root 1 minus r, sine gamma minus. So we will call this matrix, this 2 by 2 matrix is M minus. Okay? And then in place of what we've got here, we could just write M plus times the initial condition. Okay, so you combine those two, you get that after one cycle, which is 2 pi x, this equals, we'll call the matrix product M times theta 0, theta dot 0. So where M, let's be careful here, it's M minus times M plus. So in temporal order, M plus happens first and then M minus. And that's how you write the matrix. So M is just another 2 by 2 matrix given by the matrix multiplication there. Okay. This might be easier if we write it this way. I'll write it as theta dot at time t equals 2 pi x. This equals M theta dot at the initial time. So we've got theta dot, it's kind of our phase plane. And you start with some initial condition. And then this will get mapped somewhere after one forcing period. In fact, let's just call this thing, instead of 2 pi x, right, period of forcing, capital T sub f. Okay, so this is after one period of the forcing, and then maybe after another period of the forcing. We're not back where we started, we're somewhere else. And so on. And this just kind of keeps on going. Okay? So we could even write it this way. Theta dot. After n forcing periods, where n is an integer, this is going to equal m raised to the n power times that initial condition. So that's a really convenient way to write things. This first one, I'll just highlight it in red because I'm going to have to end soon. This is sometimes called a stroboscopic map, because it's as if we're looking at, I'm kind of jiggling the pendulum up and down periodically, and we are looking at a snapshot of the angle and the angular velocity after each forcing cycle. And then in this case, kind of just plotting it on a phase plane. So because we're mapping as if we're strobing with the light at the forcing frequency, it's called a stroboscopic map. And then you could extend that to looking at what happens after n periods of forcing. So this, one of the main things here is this matrix M. It seems like M is very important. So knowing the properties of the M matrix is actually going to tell us about solutions of our system. And I'll just give you a hint. M has a property related to Hamiltonian systems. M is a symplectic matrix, which means that M transpose JM. You work out that matrix multiplication here, J is 0, 1. This is what you'd have for a single degree of freedom system. This equals J, which implies some things about M, like determinant of M is equal to 1. So the map is area preserving. Small initial rectangles will not grow. And there's other things that we'll say about M, but I'll just save those for next time. So we'll say more next time, basically about, right, M as a matrix is a function of the frequency and the amplitude of forcing. And some combos of X and R lead to stability, and some to instability. Instability here would mean the pendulum flies away from equilibrium. So it's kind of you could do some interesting things there. And then look at a real, this is kind of a toy example because we've got this square wave situation. If we instead go to a sinusoidal wave of forcing, which is more like me doing this, the phenomena actually linger around. So you get the same kind of phenomena. So we'll talk about that next time. That's it.